Okay, I wanted to show you one of my most recent projects. I'm probably going to make a few videos on this, but this is the point where I turn the scratched together prototype into something a little bit more solid. What we're looking at here is a regulator, a linear regulator in fact. Pretty much one of the simplest circuits that you can use to regulate voltage using transistors and Zener diodes. But it has a few refinements that make it more suitable for use in a solar power situation. So first of all, let's start at the guts of it. This box here contains 5 of these 2N3773 power transistors with emitter current sharing resistors in there. That's my power transistor. That yellow terminal there is the base, or the bases of them. That's the collector, and that's also the input straight from the solar panels or through a diode, and that's the output, the emitters. So this is the actual regulator that's controlling it. There is a 12 volt Zener diode which clamps our reference point, and here, this transistor here is the error amplifier transistor, and this 33 ohm resistor here, which is probably slightly overkill in terms of its wattage, but it's good to make things big and heavy when you're doing solar stuff. That is the turn-on resistor for these. So it's your basic series regulator circuit with an error amplifier, just a couple of transistors, you know, nothing special there. But the refinements are, this error amplifier is not an ordinary power transistor, it's a Darlington, which for no other changes, that gives me heaps more gain, so heaps more error amplification, which means better regulation. And it also helps to do something else which is very important, which I'll get to as well. Now, like most of these circuits, I started out with the feedback voltage just through a pot, and then so you could actually adjust the voltage up and down. But once I got it to where I thought I should have it, I decided a different approach might be necessary. So this is where things get different. So normally you'd have this connected to the positive voltage of what you're trying to regulate, the load side. This connected to ground, that's the 2 wires across the pot. And the wiper wire here would be connected to the base of your error amplifier. That's the normal setup. So what I've done is I've actually dispensed with the pot. It's not really connected at the moment, and instead I'm using these diodes. So this wire here feeds 12 volts, well, the voltage from the battery, which I'm trying to maintain regulation to this diode. And at the moment I've got it set for absorption, so I've got this diode connected to this diode, and at this point here, that's the wire which feeds the base of the error amplifier. And on the other side we've got this resistor here, which as you can see is a bulb connected to earth. And the reason why I'm chosen a bulb here is because of the constant current, or near constant current characteristics of a bulb as opposed to a normal resistor. So the idea being, if you keep the current relatively constant through these diodes, then the voltage drop across them will remain relatively constant. So again, better regulation. But really accurate regulation is not necessarily that important for a battery. You know, within you know, a couple of tenths of a volt is near enough. Some people might dispute that, but in reality it's not that important. So the accuracy of regulation is not my main focus here, although the circuit is good. What my main focus is, and now is near the end of the solar day, so it's about the only thing I can really show. Here's the voltage on the batteries. Now it should be regulating at the moment at 14.5, but there's just not enough energy coming in from the solar panels at the moment to satisfy the load and maintaining that voltage. But here's the really cool part. I can remove the regulator from the circuit. I can disable the regulator, and that voltage will not fluctuate, which means that the regulator is not pulling the voltage down, which of course it shouldn't. There we go, it just fell off by itself. As you can see, the voltage is still 13.7. I'll put the regulator back on. The voltage is still 13.7. A little bit of fluctuation as it readjusts itself, but that's important. Now you may be wondering why I'm so excited about a regulator that's not regulating. Well, the idea is, of course, you don't want the regulator doing anything until the regulation voltage is reached, but when you build these circuits how they would be normally, because of the knee of the transistor's turn on curve, it starts to influence the voltage way before the regulation voltage is reached. So, and for a solar power setup, that's really shitty, because you could have a slightly cloudy day and it's gone into regulation mode, but it's not allowing all of the power to get to the batteries because it's trying to regulate a little bit. Well, on a day like that you don't need any regulation, so that's what's so cool and exciting about this circuit. For a linear regulator, it knows when to butt out and just let the full voltage of the solar panel come through the pass transistors here and hit the battery. So that's why it's like that. I guess the next question you might be wondering is, why am I building a linear regulator? Why not a PWM? Well, basically because I can. Because I have this nice bunch of power transistors here, so building a regulator like this is no problem. And also because linear regulators do have some tremendous advantages over switch mode regulators. And the main one being is that they don't introduce switching noise onto your inverters, which invariably gets onto the mains and invariably onto your loads, and that is quite a prick when you're recording heavy metal guitars. So a linear regulator is a lot more quiet. And then someone will be going, well, you know, but they're not very efficient. They're not very efficient. Well, that's true. When a linear regulator is regulating, it is dumping the excess voltage as heat across the power transistors. That's why there's a big booty heatsink here and a big fan on here. And these get quite warm at times. But my argument to that is that these are regulating power from a solar panel, and that excess power is power that wouldn't be used for any batteries or any loads anyway. So with this regulator, it will dump that excess power as heat. With a PWM controller, it will simply not take that power from the panel. So the net result is the same. That power is not being used usefully either way, so it really doesn't matter which circuit you use. The only advantage in this case over that a PWM has over a linear regulator is that it can be built with a lot smaller and cheaper components, and that's important when you've got a manufacturer in the PRC who wants to, you know, make something like this, you know, and sell it for a reasonable price, and it doesn't need a big heatsink sticking out of it or anything like that, you know, because the power transistors, which are MOSFETs in this case, are only switching on and off. You know, even my little add-on circuit here, you know, this could probably switch easily 10 amps, maybe 20, and it just needs this little sort of area here. It doesn't need a massive fan or anything like that. It's one device. So this panel, which acts as a heatsink, is clearly overkill, but I digress. So my point being is that I'm not building this to go into production in China and sell these to every man and his dog. I'm building it for my own needs, for myself, using components I largely already have. So I've got no incentive to optimize the design for cheap construction. Instead, I'm building something that works really well and is gratifying to myself in the things I like to build. So that should answer that one. Even to the point of where I just like little incandescent glowy things, you know, so any excuse I have to use one of these instead of a resistor, you know, I'll often take it, you know. Look, there's one over there, you know. Oh, I've left the meter on, it's beeping at me. This is going to be a 10-minute video on a regulator. I was hoping to keep it more concise, but what can you do? I'm not going to edit it, so I'm making this video right now because soon after I make this, I'm actually going to pull all the stuff off here, and I'm going to start to actually build up the final version of it without having all these clip leads and stuff. I've still yet to devise a circuit which will automatically take one of these diodes out of circuit so it can switch from absorption mode to float mode, but that'll come. The main thing at the moment is that I get this regulator built up and working well, which it already is working well, and then I can go on with my battery replacement program, which I'll talk about in a separate video.